Welcome back to another tutorial. Today we are going to recreate 2048. This is a casual puzzle game where you slide numbered tiles along a 4x4 board. When two tiles with the same value collide while moving, their numbers add up and merge to a new tile with that value and subsequently increasing your score. The game goes on until the board is completely filled with tiles that can't combine with one another. Originally created by Italian web developer Gabriele Cirulli over a weekend, 2048 went on to become a recognizable game due to its simple mechanics and addictive gameplay. And in this video, we are going to fully make this game from scratch in Fancade. Now that's all said and done, let's begin the tutorial. Before we start though, I do have to preface two things. One, I will mess up a lot of things during this video. This is a big project, so a mistake will be inevitable. So to compensate, there will be a visual indicator that pops up at the corner of the screen every time I do something wrong. I'll address these issues at some point during the video. Two, if you take a quick glance at the length of this tutorial, you can probably deduce that it's going to get quite complicated. Don't worry though, as I'll try my best to explain every step in the process. There's also a GitHub link in the description that contains not only the code screenshots, but a glossary of all the variables used in the game and their definitions. Okay, so we have an array of colored boxes. Each of these colors represent a numbered tile with a power of 2, starting from 2 all the way to 4096. Any value higher than that will keep reusing this red tile. We also have this block, which serves as the cell for our 4x4 grid, as well as this brown cube for the board. The first thing we'll do is to create the digits to display on top of the tiles. The key is to jam-pack them into a single block to save space in custom blocks, wherein we unglue each layer so that they don't attach to one another. We also started from 0 to make it convenient when storing these numbers into a list, as indices begin at 0. Once done, make sure that it's a physical block to easily center them when positioning. Next, let's create a script block to contain all of our assets. Inside, add a place sensor to run this code at the start of the game, and save our digits to a list. You can use the trick of plugging list elements to each other with an index of 1, as these indices add up, allowing us to get the second term and above. Then comes the painfully tedious task of assigning each digit to an item in the list. Make sure to cover all layers with pink arrows. After that, let's bring all of these colored tiles and bring them inside. Then, we'll set up a variable that determines the number of boxes we've made, in which we have 11 because remember, we start from 0. Then, let's store all these tiles into a list. Let's now create the board. I'm going to make a 14x14 square out of this block. Next, grab the board and the cell and place them inside. Then, assign them into their variables. Now that we've taken care of our assets, let's bring in another script block to store all of the main stuff, as well as place a block here since without it, we'll be seeing script blocks and raycasts even when we're playing outside the edit mode. Let's bring in a place sensor and initialize our origin point. Next, let's reveal our board and place it to where our origin point is. Then, we create a new variable that determines the board position, which is ironically going to have an offset from where the board is. We'll use this when we place our cells. Then, let's run a loop that goes on for 16 times as that's the number of cells in a 4x4 grid. From here, we spawn a cell block and save it to a list. Also, these two variables are different as one can be accessed anywhere in the level, while the other can be accessed within the script block. Then we'll be retrieving our x and y positions based on the loop index. Essentially, the x value wraps up every 4 units and the y value changes every 4 units. So, we can use a modulo for x and a division by 4 for y. We will also have to floor it so that the first 4 items are at row 0, and then so on. Then, we add a new vector when we have an offset from the board position based on our x and y values. We will be subtracting them by 1.5. Since we have 4 rows and 4 columns, we divide that number by 2 and subtract by 0.5 to get the middle value, which is 1.5. We'll then scale the offset with our specified spacing, in which we'll initialize to be 3.1325. Then, save that vector to a list. Let's loop through all of the cells and use that list to position them. While we're at it, let's also set up the camera. Set our origin point as the position, a rotation with 85 as the x value, and a distance of 75. We'll use that rotation to our light to get rid of the shadows. I'll also add in a set score block to display the score. When we press play, you can see that our board and the cells are neatly arranged. However, we do have to change the origin point to be far away, though you can also just change the visibility of that one block. Next, let's start working on the spawning mechanic. We'll trigger that event using a boolean which will set it true when initializing the game. Then, let's add an if condition here that checks if that variable is true. Let's talk about how we're going to implement this feature. Given a 4x4 board, we'll pick a random cell within that table and define it as the spawn point. Then, we generate a new tile. There's a 90% chance of it being a 2 and a 10% chance of it being a 4. Now we have two options when choosing our position. The first method is simply selecting a random cell and checking if there's a tile occupying that space. If there is, then we look for another one. We essentially loop for X amount of times until we find that free spot. This works, although in situations where there are only a few available cells left, it is going to take a lot of iterations finding those which may affect the game's performance. The second method, which we'll ultimately use later, involves scanning each cell within the grid and if they have a tile on top. If they're free, then we add those cells into a list. At the end of the loop, that is when we'll choose a random cell within our list, as we know that all of these spots are available. Going back to our code, when this boolean is true, we set it back to false to only run it once. We'll then have a loop that goes for 16 times and have a variable free set to 0, which acts as the list length of free spots. Inside the loop, we keep track of the index and the cell position. Let's bring in another truth variable set to false as we loop through the list of tiles which we denote with tslen as its list length. The idea is that we set this variable to true once we find a tile that occupies that cell. We will be using an OR block, as once this boolean becomes true, then it will always remain true afterwards. We'll need two conditions to have a valid case. One, if the tile position is equal to the cell position, and two, if that tile actually exists, which we check via an equal objects block. Leaving the second input unwired allows us to check if this list element hasn't been assigned to an object. Thus the reason why we invert that value. At the end of the loop, we check if our boolean is false. If it is, that means we found a vacant cell and therefore we should add it to our list and update the free variable. Once we've scanned all the cells, we check if free is greater than 1, aka if there are 2 or more spots available. If this is false, then the spawn cell will take up the last remaining cell and our board will be completely filled. In that case, we set the boolean check to true to check if the game has no more legal moves, which we'll take care of sometime near at the end of this video. Next, let's determine which type of tile we'll create. We have a 0.9 chance for 2 and a 0.1 chance for 4. We'll take a random block and leave our inputs unplugged to have a range be between 0 and 1. Then, we subtract the value by 0.9, making it 0 or negative if it's less than or equal, and positive if higher. We then find the minimum output between that number and 1 to clamp those high values, and the maximum output between that number and 0 to clamp those low values, before topping it off with a ceiling block to round that value up. This entire chunk of code is basically a greater than block. We just eliminated the need of an if condition. If it's greater than 0.9, then we get 1, otherwise we get 0. If you pay close attention, these are the indices of our first two tiles. Then, let's retrieve a random item for our list of free cells and assign it to our variable. Let's create a custom script block for spawning the tile, as we'll be reusing it some point later. We'll need two inputs for this block. The tile type, basically if it's a 2 or a 4, and the tile position, which is the available cell position. We'll also add in before and afterwards to integrate with the rest of our code. To create an input or output wire, all we have to do is to drag one to the side of the block. For the type, we'll be getting the lower value between the input and the number of tiles so that we can reuse the same red tile for the high values. Let's also rename these Ys. Next, create a copy of the tile based on the input type and save it to a list. Use our vector input as the tile's current and goal position. And store the tile type to a list. Next, let's figure out the value of this tile, which we know will be a power of 2. Which means we'll be using the power block. Let's say we have a number that we want to multiply by itself for X amount of times. For example, what if we want to do that to the number 2 for 5 times? We know that 2 times 2 times 2 times 2 times 2 is equal to 32, but we can also write this so that 2 raised to 5 is equal to 32. The number right here is what we call the exponent, and our original number is what we call the base. We can say that 32 is a power of 2. And that is basically what this block does. It raises a number to the power of an exponent. So, let's use our type input as the exponent for 2, but make sure to add a 1 first to get a 2 or a 4. Next, let's work on creating the digits. Hypothetically, we could have made some blocks to represent every power of 2, but that seemed quite inefficient. Instead, I think this is the perfect time to talk about how to create a number counter. Although I'll dive deeper on how it all works a little later, here's all you need to know about how we're going to do it. Given a value, we loop through each digit and find a corresponding number block to create a copy of. We then keep track of its order within the number, right to left, to position these digits later. Let's set the length to 0, which is the number of digits this tile has. And the first thing we need to do is to find the number of digits the value has. And for that, we'll be using the logarithm block. Let's return to our previous example, wherein 2 raised to 5 is equal to 32. If we graph this function, then we have this curve that goes exponentially upwards. If we try to find the value of the graph when x is equal to 5, we get 32 because again, 2 raised to 5 is equal to 32. But let's say we want to work backwards. What if we have a value of 32 and we're trying to find the exponent? Consider this curve. If we check where x equals 32 intersects with the curve, we get 5. This inverse to the exponential function is what we call a logarithmic function. In fact, we can rewrite our example as the logarithm of 32 to base 2 is equal to 5. That is essentially the purpose of this block. It outputs the logarithm of a number by a given base. We'll be using a logarithm with 10 as our base, flooring it and adding by 1 before using it to a loop. If we quickly bring this onto the level floor and test out some values, it outputs the number of digits they have. Every power of 10 is basically 1 plus some number of zeros. Say we have the number 17. We know that it's greater than 1, we know that it's greater than 10, but it's not greater than 100, which is 10 squared. So, the value we'll get is a number between 1 and 2. That's why we floor it to get rid of the decimal and add by 1 to get our number of digits. We'll also be using the same principle to determine the place value, which allows us to get each digit within a given number. We'll divide the number by a power of 10, round down, and attach it to a modulo of 10 to wrap our values between 0 to 9. Let's say we have a value of 1024. We know that there are 4 digits, so we loop 4 times. Since we start from 0, 10 raised to 0 will just be 1, so dividing it to the number won't do anything. We then run it to the modulo and get the number 4. For the second iteration, we'll be dividing it by 10 to get 102.4, which is rounded down to 102 to get rid of the decimal, which is then wrapped to the number 2. For the third try, we'll be divided by 100 so we get 10.24, which becomes 10 and ends up becoming the number 0. For the fourth attempt, we'll be divided by 1000 so we get 1.024, which then closes out at the number 1. With that being said, let's place down the script blocks. After we've created our copy, we save it to a list and lock its position and rotation to make it static. Now, let's talk about the list itself. In my previous tutorials, I've talked about 2D lists and how it can be represented as a table of rows and columns, wherein each sublist has a fixed number of elements. However, this concept does not work in our situation, as the number of digits per tile is completely dependent on the tile's type. Some tile can have 2 digits while the others can have 4. As a workaround, we could have a separate list purely to keep track of a digits list group and index. The first tile has 2 digits, so these numbers belong to group A with indices 0 to 1. The second tile has 4 digits, so they belong to group B going from 0 to 3. Although they are all stored in the same list, we use these two properties to separate the numbers and bring them to their respective tiles. Let's specify the digit order to be the loop index and the digit tile to be the tile list length. Before increasing the digit length and the list length. At the end of this loop, we specify the tile's number of digits based on our length variable, increment the list length, and connect it at the bottom of the script block. Return to the main code and attach a module along with its inputs. Next, let's position our tiles and digits, starting with the tiles. Loop to the list and check if the object is still present in the game. Then, set its position based on the tile current position with a Y offset of 1. For the digits, again, we check if the object exists. If it is, then we get the digits order, tile group, and tile length and store them into variables for convenience. Now, let's check if the tile the digit belongs to is still in the level. We'll be deleting these tiles at some point when they merge, so we don't want these numbers loitering around when that happens. Therefore, we delete them as well. We'll be using our variables to determine the offset of our digit from the tile block. Set the Y position to 0.5 to move it upwards, multiply the length by 0.5 and subtract by 0.5 to get the midpoint, before subtracting it with the order to go from right to left. Let's also adjust the spacing by 0.5. When we press play, you can see our digits displayed on top of the tiles. Hi, so turns out a game of 2048 always begins with 2 tiles placed on the board. So, what do we have to change? Remember this boolean? Yeah, that's gone. Instead, we just add 2 place sensors and attach them both here. That way, we run this code twice at the start, thus adding 2 tiles. Now that's out of the way, please just disregard the fact that there's only 1 tile to start. Next, it's time to set up the controls. Create an if condition that checks if the player has made a move. If this is false, then we attach it to a swipe sensor. On swipe, save the direction to a variable and set a boolean to true. Before we do anything to the tiles, we first need to initialize the cells. What we'll do is to loop to each cell and check if a tile is occupying that space. If there is, we take that tile's type and assign it to be the cell's value. For example, a vacant cell will have a value of -1, a cell with a tile of 2 will have a value of 0, if the tile is 4 then it will have a value of 1, then so on. We'll also implement another property to our cells, to keep track of which tiles are occupying their spaces in case of a possible merge. Have a loop that runs 16 times and keep track of the index and cell position. Initialize the cell value to be -1. For the cell set of tiles, we can cleverly use a vector to act as an array that holds 3 items, one for each coordinate. The X position will contain the ID of the tile above, and the Z position will contain the ID of the tile that will merge with the former. For now, we initialize it to be -1 at both coordinates. Then, let's define a new variable max to be the list length and set it as the loop amount. Inside the second loop, we check if the tile actually exists and if its position matches with the cell position. If both those things are true, then we take our index and update the max variable. This is what we consider in programming a break statement. Since we've updated our endpoint to be the current index, the loop now thinks it has reached the end and therefore it terminates itself. That means we don't have to loop further as we have already found our match. After that, we update the cell value to be the tile type of the found block. And add a new property to the tile to keep track of the cell it occupies, in which will is set to be the cell's index. This is done so that we have a two-way connection between the tile and the cell. We'll also add another boolean property that tells the game that the tile is moving. Finally, we update the cell set of tiles by using the index as the X value. Once we've gone through the cells and initialized the values, let's add another loop for the cells. We'll trace a raycast on top of each cell and check if it intersects with the tile object. If it does, then we'll use the swap direction to check if A cell towards that direction is empty and the tile can go there, and B, a cell is occupied by a tile with the same value. We'll also be using the swipe direction to prioritize the tiles closest to the edge. The reason being, if we started with a tile at the opposite end, the cells and tiles it checks are very much subject to change. If we started from the edge, however, then all the cells and tiles it may come across is already in their final states and positions. Let's take the index and get our x and y positions by using a modulo, a divide, and a floor. Use a look rotation to convert our direction to a rotation. We then create a new vector variable, wherein we add an offset to the board position. Use the x and y positions for the offset. Don't forget to subtract the values by 1.5. Scale it with the spacing, and rotate it based on the direction. Once we have our vector, run a raycast at that point going from top to bottom. If this raycast hits something, then we save that object to a variable and loop to the tiles. Here we check if the hit object matches with the list item. If it does, then we take the tile's goal position and assign it to the new variable and set the max loop amount to y. Now, this is the part where we start inspecting each cell within the tile's path. Even though there are situations where the board is essentially rotated due to the priority stuff, we really only have to worry about the y value when looking for the spots in front of the matched tile. Keep track of the index. Let's copy this bit of code and ignore the spacing, replacing y with I2. Once rotated, we break that vector. To retrieve the new x and y positions, we add x by 1.5 and round. For the y, we subtract by 1.5, negate, then round. We then multiply the y position by 4 before adding it with x to get a cell index. Next, let's get a cell position and save it to a variable. From here, we check if the cell value is either -1, meaning that it's empty, or if it matches with a tile type, meaning that the tile can potentially merge. If that's the case, then we set a boolean to true and loop to the cells in between. We basically don't want to move to that point if there are tiles blocking the way. We then subtract the max variable with I2 and 1 as the loop amount. Use an AND block so if ever this boolean becomes false, it will remain false for the rest of the loop. We then copy all this code and connect it here. We use the index to get that cell's value and check if it's empty. We'll also replace this bit with y minus the index plus 1, allowing us to check the cells in front of the tile excluding the goal point. At the end of the loop, check if the boolean is still true. If it is, then that means we're good to go. Add an if condition checking if the cell set of tiles x position is -1. If so, that means the cell is empty and we're free to move there. Update the set's x value to contain the tile's ID, and save the tile tab to the variable I3. If it's not empty, then we check the z position. If it's -1, then that means we're free to merge with the tile at that cell. Update the z value with the tile index, and save the tile tab with an increase of 1. Let's also bring in a new boolean property for the cells, indicating if the pair of cells have merged and set it to false. The reason why we don't do anything if z is a value is because according to the original game's mechanics, a resulting tile cannot merge with another in the same turn. Update the max variable to break the loop and connect it to both conditions. Update the new variable to the new cell position. Once a tile is moved, we have to update the cell values of the original cell and the new cell. First, let's reset the former cell set of tiles as nothing is occupying that space anymore. Then, we'll use I3 to determine the cell value of the new cell. The first condition only saves the value of the moving tile, and the second condition has an increase as 2 tiles merge in that cell. Set the original cell's value back to -1 and update the tile cell index. At the end of everything, we check if the tile goal position still matches with a new variable. If it doesn't, then we update its value. Next, it's time to code the actual tile movement. While this boolean is true, we set a truth variable to true before looping through all of the tiles. Within the loop, make sure the tile is an actual object. Then, use an end block to lock the boolean to false if it happens, and check if the distance between the current position and goal position is less than a new parameter, which will also act as the movement speed. Initialize it at the start to be 1. We'll also add an if condition. If this is false, then we have to update the position to move towards our goal point, and to do that, we will be using the normalize block. What this block does is it outputs a vector with the same direction as the input vector, but with a magnitude of 1. Vectors with lengths of 1 is also known as unit vectors. Say you have two vectors, both of which are represented by these arrows, and they point towards the same direction. The difference, however, is that one is clearly longer than the other. By normalizing these values, we keep the directions but change their magnitudes to be of the same length. This block is useful if you only care about the direction of a vector. In our case, we don't care so much about the distance between the two positions, but rather which direction to go. We'll update the tile position by adding it with a normalized offset between that and the goal position, and scaling the value with our speed variable. Once the distance is close enough, we check if the moving boolean property is true. If it is, then we set it back to false and update the tile position to be where the goal point is. Let's have another loop, this time for the cells. Fetch the set of tiles x and z positions, and inspect if both of them possess a value other than -1. If that's true, then we have two tiles that we have to merge. We then check if the tile with the z ID has stopped moving, and if the cell hasn't merged the two tiles yet. If so, we update the boolean to true and keep track of one of the tile's positions. We then delete the two tiles which consequently also delete the digits before adding a new tile. We'll use the cell value for the type and the cell position for the vector. We'll also position the tile to be where the previous tile was. To get our tile, we simply subtract the list length by 1 and use it as the index. Next, we increase the score with the power of 2 raised to the cell value plus 1. So if two tiles with a value of 4 merge, our score increases by 8. Finally, let's add some plop s effects, with a random pitch to give variety. At the end of the loop, check if the truth variable is still true. If it isn't, then that means at least one of these tiles are moving and therefore we set another boolean to true, which determines if the game can spawn another tile. The reason being, we don't want to generate anything if the player hasn't technically done a move. Once this is true, then every tile is in place and we check our new boolean, before setting our moving state back to false. If this is true, we reset the variable, then trigger the spawn event. And if we press play, everything is completely broken. Have you paid any attention to that indicator? Can you pinpoint the various mistakes I've done throughout the video? If not, then let's go ahead and mend our errors. First, this index at where we look for cells in front of the chosen tile has to be I2, which is the actual loop index. The same thing goes here. Then we need to set the x and z positions of our cell tiles to be -1. We also have to change this variable to be I2. Finally, this has to be there instead of some vector variable. Now, when we test this out, the movement seems to be working. We can slide our tiles around and merge with tiles of the same type. Oh! Turns out, inside this module, I forgot to save the loop index. Let's quickly fix this. Now, at long last, everything is operating smoothly. Except, not quite. This was something I caught while I was editing the tutorial and it's pretty game-breaking. Remember when we were setting up the module for spawning tiles and how we used the minimum value between the input and the number of tiles? I didn't really think about testing what would happen once we have the red tile since the chances of a player reaching that point is quite slim, but essentially that value just stops at 496, because, oh, well duh, of course it would. What I should have done is put this bit at the list index, so although we were using the same red box, the number still doubles. Take note that every instance of the block will be disconnected if you mess with the input bars, so just quickly rewire them. Now that I got that sorted, let's return to the actual video. Eventually though, these tiles will slowly fill up the board, and before you know it, there are no more possible moves. That's why we need to implement a mechanic that checks whether a player can still make a move or it's game over. If you remember earlier, we have set a boolean that becomes true when the number of available cells is less than or equal to 1. Now, place a late update sensor to have this code run once everything has been positioned properly and check the truth variable. If this is true, then we set it back to false to execute once, and add another boolean set to false. The idea is to loop to each tile and draw a raycast in 4 directions to look for adjacent blocks. We then check if the detected tile has the same value. If it does, then that means the player can still make a move by merging them. Create a loop, save the index, check if the object exists. Save the position, loop 4 times, take the index and multiply by 90 before attaching it to the Y rotation, covering the cardinal directions. Using the tile position as the starting point, add a rotated offset of 1 in the x-axis. This is done to avoid detecting the tile itself. We then add another rotated offset which is killed by the spacing. If there is a hit object, we loop to the tiles and look for the match. We also have to check if the tile types are equivalent. If that's the case, then we set the boolean to true. At the end of the loop, we check the variable state. If this remained false, then that means the player can no longer make a valid move. So we connect it to a loose block and a beep sound effect. If we playtest this and go until the board is completely filled, we trigger the loose condition. We have finally reached the end of this tutorial. This video is definitely a lot more complicated than usual, so if you managed to recreate this game then congratulations! I hope you learned a lot of new info and concepts with this tutorial that you could use when you make your own games. As always, there's a GitHub link for the code screenshots, plus the new glossary of variables used throughout. Thank you for watching, and I'll see you at the next one.